combustion of 0.57 gram of a hydrocarbon produces 1.79 gram of carbon dioxide. If the molar mass of the hydrocarbon is 56, we're given the molar mass, find the molecular formula. This time around, this is the molecular formula. And of course, we know the molecular formula will be derived from the empirical formula. So invariably, our target is to establish, first of all, the empirical formula. So the empirical formula is our first port of call. Empirical formula. We're going to have to establish this first. Then make use of this, combine with the molar mass, and then we can have the molecular formula. All right, let's get straight into the solution. First, we perform this calculation. 0.57 gram of the hydrocarbon. A hydrocarbon is an organic compound that contains carbon and hydrogen as the only constituent elements. So we have what leads us to the mass of carbon present, 1.79 gram of carbon dioxide. The question is, what mass of carbon will be present in 1.79 gram of carbon dioxide? Let's talk about it. So we're going to use the method of dimensional analysis for that. Let's start with 1.79 grams of carbon. Now we have to multiply so that we can strike out this unit. The denominator is the place to go. Gram of carbon. So we have to find a way to strike this out. How do we do that? We look at the molar mass of carbon dioxide. In a rough area there, the molar mass of carbon dioxide, we have carbon dioxide is CO2. So quickly we can get the molar mass of carbon dioxide. Molar mass of carbon dioxide will be the relative atomic mass of carbon, 12, added to that of oxygen, which is 16, but we have to multiply by 2 because oxygen occurs 2 times. And this will give us 60 multiplied by 2 gives 32. 32 plus 12 gives us 44. So the 44 is the molar mass of carbon dioxide. This 44 is made up of 44 grams per mole. So 1 mole of carbon dioxide has a mass of 44 grams. Of this 44 grams, 12 is contributed by carbon. So this 12 here is the mass due to carbon, while the 60 multiplied by 2, 32, is the mass due to oxygen. So invariably, we're saying 44 grams of carbon dioxide contains 12 grams of carbon. And we can make it down here, 44 grams of CO2 contains 12 grams of carbon. That's right. And we've achieved our goal. As you can see, gram of carbon checks through gram of carbon. Oh, this is carbon dioxide, 1.79 gram of carbon dioxide. So we have CO2 actually here. So gram of CO2 is knocked out by gram of CO2 right there. And the surviving unit is gram of carbon. By multiplying this using an electronic calculator, we get our value 0.49 gram of carbon to 2 decimal places, of course. Now we know the mass of carbon present, and therefore it means we can know the mass of hydrogen present. The hydrocarbon has a mass of 0.57. So this is mass of carbon. Mass of hydrogen will be the difference. We have 0.57 subtracts 0.49. This is 49, of course. 49 gram is intended here. Minus 0.49 gram of hydrogen, which actually gives us 0.08 when we subtract. 0.57 minus 0.49 gives us 0.08 grams of hydrogen. Therefore, we have set up the composition of this organic compound, this hydrocarbon. Therefore, the hydrocarbon contains 0.49 grams of carbon and 0.08 grams of hydrogen. Beautiful. This is beautiful. Now we have reset the question from this complex question provided. We have reset it into an organic compound, a hydrocarbon specifically, that contains 0.49 gram of carbon and 0.08 gram of hydrogen. And now we can proceed with the empirical formula. I like to take off these traces so that we can move on. So take note, 0.49 gram of carbon and 0.08 gram of hydrogen. Let's take off these traces. Beautiful. And we are going to use the tabular formats. So let us have a table. Beautiful. Now we have the table. First, the elements. Taking that away. And the first element is carbon. And then we have hydrogen. So carbon and hydrogen. It is a hydrocarbon. And those masses we have for carbon, 0.49. And for hydrogen, 0.08. Now the next is to go ahead with the relative moles of atoms present. So we simply have relative moles of atoms. Moles of atoms present. And that will require us to divide each of these by the relative atomic masses, not the molar masses, because we want the moles of atoms. So this is 0.49 divided by 12 for carbon, and 0.08 divided by 1 for hydrogen. Beautiful. And now we really want the simplest ratio at the long run. Now we want to multiply the numerator by 100. So this can translate into multiply by 100, 49 over 12. Since we're doing this for both of them, it doesn't really change the result. Multiply by 100, we have 8 divided by 1, which is simply 8. Now, 12 divides into 49. This is approximately equal to 4, of course, while this is still 8. And now we can obtain our simplest ratio by dividing by the smaller of these two. So we have our simplest ratio. Beautiful. The simplest ratio will be taking 4 and dividing by 4, the smaller of the two numbers, and also taking 8 and dividing by 4. And this will give us 1, while 8 divided by 4 gives us 2. Therefore, the empirical formula can be written. The simplest ratio of combination of atoms is 1 atom of carbon combining with 1 atom of hydrogen. And therefore, we can write the empirical formula. The empirical formula is simply written as 1 atom of carbon combining with 2 atoms of hydrogen. This is beautiful. The first phase of the calculation has been executed. Let us take these traces off so that we can prepare for the final stage of this calculation. All right. Now we have the molar mass of the hydrocarbon is spelled out, 56. So we can make use of this to get the molecular formula. Now let the molecular formula be the empirical formula, which is CH2 multiplied by a whole number n. This is due to the fact that the molecular formula is an integer multiple of the empirical formula. Now we can simply find the molar mass of this compound and equate to 56. Let's do that very quickly. Therefore, we can say N must start the multiplication of the result in the parentheses. So carbon 12 plus hydrogen occurs twice, so 1 multiplied by 2, because the relative atomic mass of hydrogen is 1. So we're multiplying by 2, and all of this should give us the molar mass 56. And let's complete this calculation. Therefore, from within the bracket, 1 times 2 is 2. That 2 plus 12 gives us 14. 14 multiplied by n gives us 14n. And this equals 56 on the right-hand side. A simple algebraic equation in one variable. Now we can divide both sides by 14 to obtain n. So isolate n by division of both sides by 14. And this gives us, and therefore, n equals 4. Beautiful. Now we can have the molecular formula of the hydrocarbon. In the final analysis, the molecular formula, since we know the value of n, the problem has been solved. The molecular formula of this hydrocarbon simply will be CH2 multiplied by n. And since n has been determined as 4, we can do this expansion. That will be C receiving 4 with H. 2 multiplied by 4 gives us 8. Very simple. And that will be our final answer right there in the option D. Very simple. Now, attached to this video are 2 quizzes that you can attempt to test your understanding of the content of this video. In addition to that, there is a link in the pinned comments that will enable you to take a quick test on the topic, chemical composition stoichiometry. So I recommend you to take the test. There are 20 questions to be taken in 30 minutes. This will help you to establish your mastery or your understanding of the topic, chemical composition stoichiometry. And finally, if you intend to study the full presentation of the topic, chemical composition stoichiometry, you can click on the link provided in the pinned comment to study the full video. Thank you for being part of this session, and I look forward to seeing you in the next video.